Hello everybody, welcome back to another video. In this video, we're going to be taking a look at a question from IB Chemistry Paper 2HL from the May 2018 batch, and this is from time zone 2. Now, continuing on from my previous videos where I take a look at questions from topic 5 and explain some of the concepts that are important to topic 5, here we're going to be taking a look at a slightly different topic, which is entropy. Again, it's from topic 5, but it is building upon what we have previously learned. Now, just like enthalpy, in enthalpy, we measure the energy of a particular reaction. So for enthalpy change, we measure the energy change in a reaction. In entropy, we also can measure entropy. We can measure entropy change as well. And that's what they're asking us to do in this question. But before we get on to how to do it, we should first understand what exactly entropy is. What is entropy? Entropy is essentially the measure of how available energy is distributed among particles. And what do I mean by that? What do I mean by how energy is distributed among particles? Well, there are a variety of different ways that energy in a particular reaction or in a particular substance can be distributed among its particles. And this fluctuates. The distribution of this energy varies between the states. So I'm going to give you an example. Now let's take a look at water. Okay, these are water molecules. These are water molecules tightly packed together in the form of ice, right? This is water in the form of ice. It's a solid, we know it's a solid. And if we were to determine the entropy of this, we probably won't be able to get an exact number by looking at it. But since entropy is the measure of how the energy is distributed among the particles, we could deduce that the entropy for this reaction would be fairly low, or sorry, for this substance would be fairly low, because all the particles are arranged very orderly. They're arranged in a particular um, pattern like structure, right? So the number of ways in which energy can be distributed among these particles is not that many. You can't distribute it in many ways because one, they can't move, they are stuck in one place or they are bounded together. And two, even with the energy, the maximum they can do, the movements they can do is they can vibrate. That's all they can do, right? So the entropy is going to be low. There's not many ways you can distribute energy in this substance, in a solid. But now let's imagine we melt, we add some heat to this ice, and this ice becomes water. So it becomes water in this container. Now the water particles are just sort of floating around. They are slightly more free than they were in a solid. They're more free to move around. Their intermolecular forces still do exist, but they're not as strong as they used to be in the solid form. However, over here, the energy can be distributed in slightly more number of ways, right? You can distribute more energy to one particle and less energy to another particle, whereas one particle could be, more active than another particle. It's all random, right? There are more ways, the more possible ways to distribute energy in this, in liquid, in water in its liquid form. So you can deduce that in a liquid like this, entropy would be slightly higher than it would be in a solid or more higher, but we don't exactly know the magnitude. Now we add a bit more heat to the water and it becomes water vapor. So it evaporates and it becomes water vapor, which is a gas. I'm going to put water vapor. And in a gas, the entropy has to be the highest because the number of ways in which you can distribute the energy among the particles is numerous, right? And if you want to conceptualize this a bit better, I'll give you another example. Imagine that you are sitting in a hall, okay? There are 50 other people around you, and there is a person who has told all of you to sit in your chairs and that you cannot get out of your chair, but you can move around by in that position, in the position that you're sitting down on the chair. So what is the maximum thing you could do? You could pivot on your chair, but you can't do anything other than that. So that basically means that the energy that you have in you, you can't use that, and you can't use that energy to do many different things. The only thing you can do is pivot around. So your movement is limited. The distribution of energy isn't very big. There are a very limited number of things you can do. However, if the person then told you that you can stand up and walk around, well, now there are more ways that you can utilize your energy, right? So the entropy has increased. So you can walk around, you can walk backwards, you can walk forwards, you can walk sideways, you can walk I don't know, in whichever direction that you want to go. So now there is more use to the energy that you have. There is a greater distribution of what your energy is being used for. Then the person in charge tells you that now you can do any sort of movement that you want. So depending on how creative you are, some people may start crawling, running, doing backflips if if you can do that, running, walking, all of these things that I mentioned earlier. So now there are so many different ways that you can distribute the energy in a population, or within yourself, or so on and so forth. And just like that, in solid substances, the entropy is low, and I explain why that is. In liquids, the entropy is higher than solids. It's higher than solids, but it is lower than gases. And obviously, entropy in the gases is the highest. Now that we have understood what entropy is, let's take a look at this reaction, and let's calculate, or let's sort of determine what the entropy change is going to be. Now, in this question, they're not asking us to make a general comment about the entropy. They're asking us to calculate the exact value of the standard entropy change for this reaction. And they have given us the values of the entropy of these different substances that are also in this reaction, and asked us to calculate it. Now, for this, you just have to remember one formula on how to calculate entropy. It's just one formula, very simple formula. Um, it will look familiar to you because we have done it in a similar one in the previous video as well. So, in order to calculate entropy, the formula is it's all the entropy, it's the entropy of products minus the entropy of the reactants. That's it. I'm sure this looks a bit familiar to you from the previous video if you have watched it. In that, I said it was enthalpy of products minus enthalpy of reactants. In this case, it's entropy of products minus entropy of reactants. So let's calculate it. What is the entropy of the products? These are our products. Our products is hydrogen gas and carbon monoxide. What is the entropy of carbon monoxide? Well, it's 198. And we have to add it to the entropy of hydrogen gas. The entropy of hydrogen gas is 131. But since there are 3 moles of hydrogen gas, we have to multiply this by 3. And this gives us an answer of 591. What about the entropy of the reactants? Well, our reactants is water and methane. What is the entropy of water? It's 198. Sorry, 189. My apologies. And what is the entropy of methane? It's 186. So in we have to do this sum where we subtract the entropy of products from the entropy of reactants, and we get our answer as 216 joules. Now remember, the unit's a bit different over here. It is not the same as what we have in enthalpy. In enthalpy, we measure the energy change in kilojoules, but over here we measure in joules. So that's an important point that we will take into consideration later. I'll show you how that's important in the next video. But for now, that's all you need to know. That is it. That is it for this video. That's how simple this question was. Hopefully you have understood the concept, and hopefully I have managed to make your life a bit easier in this topic. Thank you so much for watching. If you have any questions regarding this concept or any other concept, please feel free to message me on my social media, send me an email, or put down in the comments below, and I will be more than happy to help you. I will see you in another video with another question. Take care of yourselves, and goodbye.